In this lecture, we're going to provide an introduction to the general topic of energy. Now, when we talk about energy, energy is one of those variables that is often very difficult to define. In addition, poses a bit of a challenge in terms of quantification. But if we go back to the history of the term was first coined by Thomas Young, who was a physician and a physicist, those that engaged in two or more professions at the time were referred to as polymaths. But as mentioned, Thomas Young was the first to coin the term energy, and that term replaced the existing term vis viva that referred to a living force. Now, Thomas Young is also known for developing an equation to quantify energy of moving objects, and that energy, quantity of energy, was determined to be equal to the mass of the moving object times the velocity of that object squared, indicating that the velocity of the object is going to play a much larger role in how much energy, movement energy, that object has. Now, the equation was later corrected by a famous mathematician by the name of Lagrange, who basically determined that the equation needed to be divided by 2. And this is now known as kinetic energy, as we'll address in this module. Now, when we talk about energy, as indicated earlier, energy is a rather elusive term to define, but we're going to define it here as an ability to cause changes in work, heat, and or mass. And a common definition that you may have likely encountered in previous science courses or physics courses is the ability to perform work. And when you think about work, think about an object that is undergoing motion. So there are different forms of energy. In this module, our focus eventually will be on mechanical energy, and that energy that is involved in moving physical objects. But we're going to have more of a general discussion in terms of the different forms of energy. Another form of energy is electrical energy, which involves in the movement of charges through electrons. Now, physiologically, we're not talking about the movement of electrons. So physiologically, electricity is generated from a well-known event called the action potential, which involves the movement of charged elements, i.e. ions, across cell membranes. And the most famous ions that we often refer to in physiology is the sodium ion, potassium, chloride, and calcium. All of those elements have a number of electrons that are out of balance with the number of protons in the nucleus that makes those elements physiologically out of electrical neutrality. We have thermal energy that we'll make reference to in this lecture. When we think about thermal energy, it's essentially referring to the kinetic activity of particles within a solid, within a gas, within a liquid or a fluid. And so that's related to an increase in that random motion and an increase in temperature. We'll discuss in this lecture the nature of chemical energy, which is the energy involved with the formation and breaking up of bonds holding atoms and molecules together. The last form of energy, which we will not address in this lecture or in this unit, but nonetheless interesting and important, is nuclear energy, which relates to the binding and unbinding of nucleons, those particles contained within the nucleus, which we know mostly as protons and neutrons, but the nucleus incorporates other particles involved in that existence of nuclear energy. Now, as it relates to biomechanics, this lecture will provide an overview of so-called metabolic energy. And when we think about biomechanics, the production of force, whether it's a static situation or a dynamic situation, all of that is carried out through these metabolic changes within muscle cells, as well as other cells in the body. And so to understand the nature of energy, be it electrical, chemical, thermal energy, mechanical energy, the first law of thermodynamics is one of many laws of thermodynamics, but is the one that governs how energy is handled within the human body. And this law states that energy cannot be created from scratch or destroyed, but energy is converted from one form to another. And when you think about those forms, think about the different forms of energy that we addressed on slide number 3. And so what you see here is the chemical structure for a molecule that is known as adenosine triphosphate, or just simply the ATP molecule. And when you think about the ATP molecule, think about this molecule as the equivalent of cellular money. And so in order for the cell to carry out many functions, the cell's going to have to spend money to move ions, to produce force, to make new proteins, and to do a whole host of carry out various functions. Now, the value of this cellular money, the value in the ATP molecule resides right here, resides in this high energy phosphate bond. And that's what we refer to as quote unquote stored energy. Chemists will quantify the amount of energy here in what they refer to as the dissociation energy. So basically, how much thermal energy has to be applied to this molecule in order to break this phosphate group away from the rest of this large portion of the molecule. And what scientists have discovered is that this chemical bond here houses a great deal of potential, or houses a great deal of chemical energy that we could potentially use for carrying out functions of the cell. So ideally, when we break this chemical bond physiologically, that stored chemical energy is harnessed, and in harnessing that stored chemical energy, it gets converted into mechanical energy. And when you think about mechanical energy as the energy involved necessary to move things, some of the things that necessitate movement is cell motility. So sperm cells, for example, have to expend energy in order to swim within a fluid environment. In order for a cell to make new protein, the cell must be in a state where it has a sufficient amount of ATP in order to allow the combustion of the ATP molecule, what's more specifically referred to as the hydrolysis of an ATP molecule, harness that stored chemical energy, and that energy will be used to make new protein. And of course, in order to produce force, be it a static situation or a dynamic situation, muscle contraction necessitates a continual supply of ATP. In order for cells to remain in a resting state, ions must constantly be moved across cell membranes, and some ions require the spending of cellular money, and that's where an ATP molecule must be hydrolyzed, and so that we can harness that stored chemical energy. Now, in an ideal world, that chemical energy that's harnessed will entirely be used for mechanical energy. However, most of that stored chemical energy gets converted to heat, or rather thermal energy. Now, in order to understand this transfer in energy involved with human biomechanics, it necessitates an understanding of human bioenergetics with respect to the formation of ATP. So, as briefly mentioned on slide number 4, we listed a number of functions that require the chemical energy in the ATP molecule. But once you spend money, that increases the need to make money. So the question here is, where will the cell make new ATP molecules? Well, it will come from a molecule referred to as creatine phosphate. So our cells have enzymes that will take the creatine phosphate molecule, break it down, and donate the phosphate component to a D-diphosphate, adenosine diphosphate, and make a new ATP molecule. The degradation of glucose, so glucose is a very important molecule in our cells that gets broken down in a number of steps referred to as glycolysis. And when we combust glucose, one of the outcomes of that is to make more money, to make ATP. Our cells are very good at that. But we are aerobic organisms, and being aerobic organisms, we have the ability to make ATP in the presence of oxygen. And so we have what are referred to as without oxygen anaerobic pathways, which are typically short-lived, and that involves the creatine phosphate pathway as well as glycolysis. But being aerobic organisms, we survive on molecular oxygen that we breathe in through the air, which sustains long-lasting forms of pathways for ATP resynthesis, and that's through a process called oxidative phosphorylation. Now, the fuel that will drive oxidative phosphorylation, that fuel comes from the breakdown products of glucose, the breakdown products of fat, as well as protein. So, in order to determine how much energy comes out of foodstuffs, a process referred to as direct calorimetry is used to essentially measure the heat production during the course of metabolism. And so here we see an example of a person standing inside a sealed chamber, and within this chamber, as the person even as the person is just sitting, they are releasing heat as part of the metabolic pathways to sustain life, and that heat is measured through circulating water, and estimates can be made with respect to how much oxygen the person consumes and how much the water surrounding the person circulating through around the chamber increases in temperature. And so by combining foodstuffs with molecular oxygen, that will lead to the formation of ATP as well as the liberation of heat. And so heat is what's measured with direct calorimetry. Now, when we talk about the foodstuffs, what we're referring to are carbohydrates, lipids, and proteins are 3 macronutrients. However, when you talk about carbohydrates, lipids, and proteins and energy turnover, we're specifically referring to the glucose monosaccharide of carbohydrates, the fatty acid of lipids, and hopefully not to a great extent amino acids. And so the human organism is capable of combusting glucose, fatty acids, and amino acids if necessary in the presence of oxygen in order to make ATP to sustain life. Now, in terms of units with respect to energy, energy is defined, is quantified using a number of different units here that may seem familiar. When you talk about nutrition, you're quite familiar with the term the kilocalorie, or kcals, is a common unit of heat that is used to quantify how much energy is in the food that we consume. And 1 kcal is equal to 4.186 kilojoules of energy. So these are international system units. that are often used, and we will use these units in biomechanics. Now, so direct calorimetry is a very difficult process to carry out in terms of estimating a person's energy usage, and so indirect calorimetry is a more common technique that's used indirectly to estimate energy expenditure by measuring oxygen consumption as an estimate of resting metabolic rate, or as you can see in the pictures here, an indication of metabolic rate when people are engaged in some form of physical activity, cycling, walking, or running. And so this follows the general premise that when we combust foodstuffs, glucose, fatty acids, amino acids, in the presence of oxygen, heat will be liberated, CO2 will be produced, as well as molecular H2O. And so this follows the equation of calculating something called VO2 that we'll address here in the next couple of slides. In terms of, as an example of VO2, the dot above the V is a very common symbol that you should make note of, and anytime you see a dot above a symbol, that indicates a time rate of change. And so what we see here with the V represents the volume of a gas. In this case, it's molecular oxygen, 2.0 liters. The dot indicates per minute. And this equates to approximately 10 kcals of energy expended per minute if a person records a VO2 of 2.0 liters per minute. And this is often achieved through something called open circuit spirometry. And in this case, as you can see, the exercising individuals are breathing through a mouthpiece. The mouthpiece is allowing air to come in, ambient air to come in. The person expels their air through this hose attached to gas sensors, and those gas sensors will detect the presence, the concentration of oxygen and carbon dioxide over the course of time during the activity, and provide an estimate of the person's oxygen whole body oxygen usage, which is essentially the difference in the rate of volume of O2 inspired and the rate at which that oxygen is expired. And so this figure will illustrate how the body's use of oxygen correlates with a measure of power that we'll address in terms of in the mechanical sense later in this unit. But this is a graph illustrating the energy cost of horizontal treadmill walking or running. In this graph, it's specific to cycle ergometry. And so as a basic rule, oxygen usage, the requirement, utilization, increases generally as a linear function of speed as a surrogate measure of power. And so in terms, another unit to express energy cost is in what's called metabolic equivalence, or METs. 1 MET is equal to approximately 3.5 milliliters of oxygen per kilogram of body mass consumed, utilized per minute. And this is taken under resting conditions. So if a person engages in exercise and that exercise is characterized by having a value of 5 METs or 5 metabolic equivalents, that person's oxygen utilization is estimated to be 5 times 3.5 milliliters per kilogram per minute. So by focusing on this graph and examining oxygen usage dynamics, we see along the bottom from left to right the work rate, which is another term for power quantified by watts, increases from left to right. So on a cycle, this is generated from an increase in cycle cadence and or the workload, the resistance against the flywheel on a bike. And the VO2 measure on the y-axis is a measure of whole body oxygen consumption. And what we see here is that as power increases, so as the cycling cadence and or resistance on the flywheel increases from left to right, the person's nervous system will have to activate more muscle tissue and the existing muscle tissue at a greater rate. Whenever we do that, that will increase cellular spending of money, which is ATP, requiring the cell to match the rate of ATP spending to the rate at which it must make new ATP. So as power goes up, the need to make ATP, the rate of making ATP and that need will also increase as well. And that will be matched by how much oxygen must be part of that process. And the way we get more oxygen is by increasing the depth and rate of breathing. And so we see this nice linear function between these two variables. However, if we continue to increase work rate, eventually the oxygen utilization, as you see here, will start to plateau and hit a maximum point. That maximum point where if you continue to increase cycling speed, there will be no further increases in the maximal rate of oxygen utilization. And so this is what the VO2 max represents. It represents a single person's whole body ceiling, maximal ability to pull oxygen in, diffuse it into the cardiovascular system, move it to muscles, and use that oxygen to make new ATP. In order to increase power output after a person achieves VO2 max, that person would have to rely on anaerobic methods for ATP resynthesis, and the ability to carry out exercise at that point will be very limited, as fatigue will certainly ensue. And so the VO2 max is achieved when this plateau is achieved. So one last point with respect to this turnover of metabolic energy is something referred to as net efficiency, which is the ratio of the work output divided by that energy expended above the resting state. So if you think about the resting state, if you're sitting there listening to this lecture and you're not moving, you are performing zero mechanical work. However, even sitting there, your body is expending metabolic energy to be alive. And so because you're not moving, your work output is zero divided by your estimated energy, which can be calculated from one metabolic equivalent of 3.5 milliliters of oxygen per kilogram of body mass per minute. Your net efficiency would be zero. So once you start moving, energy expended, metabolic energy, would certainly start to increase, but the work performed will start to increase. So your net efficiency will actually start to increase once you move from a resting state. Now, mechanical efficiency related to human movement does have a maximum point, which does vary person to person. So if we use the example of cycle ergometry, which is a convenient measure, a convenient medium in order to quantify work output, studies have demonstrated that humans are approximately 15 to 20% efficient. So that during cycle ergometry, most of the metabolic energy that we expend is transformed into thermal energy, where less than 1/3, perhaps on average up to 1/4 of all of that stored chemical energy in the ATP molecule will go towards the force production that will be applied against the pedals on the bike. And so in this sense, efficiency will certainly decrease with an increasing work rate, and it has what's defined as a curvilinear relationship, in that efficiency will start to increase once we start moving from a resting state, but then it will start to plateau and eventually will decline at very high work rates, as the mismatch between how much work we can actually perform versus how much energy it takes to carry out that work will start to be out of favor with being able to continue that type of exercise. So this ends our introductory lecture to our energy module.